This practice probability worksheet is simply provided because it contains the common distributions you would use in basic statistics all the time in a way that can serve as a very, very quick calculator if you want to use it that way. One of the ways you might want to download it and look at it is just to evaluate the syntax of the different Excel built-in functions for doing each of these. I'll just walk you through them very, very quickly. The first is the hypergeometric distribution. It's a very, very simple function for coming up with a hypergeometric distribution, which is a discrete distribution for calculating one simple discrete value. So if you look at the function for that is the hypogeomdist. If you have a different version of Excel, it's possible your function name will be a little bit different because I know the names change over time, so you might have to search for the hypergeometric distribution to get that. But it's got the basic 4 parameters of hypergeometric distribution. So in this case, a population size of 52, the successes in a population of 4, the sample size of 5, and a success in sample of 4. So this would be an example, say, of a 52 card deck where you're going to draw 5 cards and you're hoping to get 4 aces or 4 kings. What's the probability of doing that? So the hypergeometric distribution of that is 185. If I wanted out of the 4 to pick a success in sample, say I have a 3 of a kind, my probability might be that, or 2 would be that. So I can simply calculate the probability of a given discrete value as I go through. Keep in mind these are discrete distributions. It's not the population of 2 or less or 2 or more. It's just the population, in this case, of probability of getting 2. The next probability over is the commonly used is the binomial distribution, where you've got any kind of experiment where something can happen or not happen, or success or failure, or defect or not defect, some kind of a binary state coming in, and you know the probability of that happening. So there's a function in Excel for calculating that, which basically is the number you're trying to get, the probability of getting, in this case, 2 out of a population size of 5 with a population of 0.5. The false means you're looking for just the probability of getting the 2 as you go in. If you put true in that last parameter, you're looking at, in this case, 2 or less. So n is the sample size, p is the probability, d is what you're looking to get, and a false or true use of the built-in function will tell you what the probabilities are. So if I have a population of I'm going to do 5 trials with a probability of 0.5. What's the probability of getting 2 successes? The probability is 31%. What's the probability of getting 2 or less? So 0, 1, or 2, it would be 0.5. So I could get that number if I wanted to. I could take the probability of 0, which is about 3%, the probability of getting 1, which is about 15%, the probability of getting 2, that's 31%. So I could discrete by discrete go through and get that, but the Excel function for looking at the cumulative probability works very, very well. So basically you've got the either the probability of a single value or the probability of it being less than that. Subtract that last value from 1 and you've got the probability of being more than that as you go through. The third distribution in a discrete distribution discussion would be the Poisson distribution, the probability of a more or less randomly happening event showing up. This isn't just the probability of any event. It has to be a naturally occurring random event. So it might take some practice for you to get used to doing that. This distribution is based on E, the natural log. We need to know how many we expect, and then we conjecture how many we're going to see. It's like other discrete distributions. Poisson, you're looking at the probability of a given value going through. So if I wanted to know the probability of multiple values, I would use this function more than once. In this example, the conjectured value is 990. So if I have a Poisson-based event that I expect to have happen 1,000 times per unit, and this could be a day, a week, a month, there's no time sequence documented here, what's the probability of actually getting 990? Well, the actual probability of getting exactly that number is only a little more than 1%. But the probability of getting that number or less is roughly 38%. The probability of getting that number or more is roughly 61%. And you expect a larger percentage to be in the direction of the expected value. So 38% chance I'll get 990 or less as I go through. So if I'm a bank manager and I want to put, and I'm expecting, say, 100 customers per hour, I might say, what's the probability of getting exactly that 100. Well, I have a 52% probability of getting less than 100 and a 47% probability of getting more than 100. So I can do my capacity planning, things that way as I go through. The last distribution that we don't normally use in a discrete chapter, but I'm only mentioning here, is going to be the normal distribution, which we would move to when we go to cumulative distributions. The reason we talk about the normal distribution at all in the context of discrete probabilities is that as your n gets larger and larger, the binomial and the Poisson distributions become less refined in terms of their discreteness. They actually start to look and become approximated by the normal distribution. So here in the spreadsheet, I've given you the logic for doing a normal approximation of the binomial and the Poisson distribution as you go through. So you can play with that if you want. And the actual factors of calculating the probability for a normal distribution, you would pick up in a unit on continuous distributions. So like I said, I only mention it here because the normal distribution is an excellent approximation for the binomial and Poisson distributions as n gets very, very large. That was more important in the past where you had to do these calculations yourself, because we tend to have Excel for doing calculations nowadays. You'll find you rarely need to use the approximation because the Excel built-in function can handle any arbitrary large size as you go through. The other tabs of this spreadsheet, just so you know what they are, is just going back again to the hypergeometric distribution individually if you want to play with that, showing the formula. The binomial distribution where you can plug in an n and a p and it will show you the graph. So if I change, so if my n is 14, my probability is 0.5, my expected value is in here at roughly 8. It's the peak of the distribution, obviously. I expect to see values ranging from about 1 to 15. So then that's reflected in the cumulative probability over here on the right. By the time I get up to 13 to 15, I expect to be at a probability of 1 for that expected value. So you can play again with that value, maybe change your n, change the probabilities as you go through. You want to really see what different curves look like as you go through. It's just a way to graph it. And on the Poisson side as well, playing with what is your lambda. If you expect something to happen 29 times, and realistically, it's going to happen most often between 21 and 41 times, and the cumulative distribution shows that. So again, if I change the distribution, say I expect 15, you'll see what that curve looks like. So the last three tabs are just a way to play with the data. But realistically, these are the basic built-in functions in Excel that you'll need when dealing with discrete distributions. So if you take a look at just how the formulas work, you'll find it much, much easier to build into a spreadsheet.